This is a B-Day Friday. So we will have class on Wednesday only this week. So if you need help outside of just Wednesday, email me. We'll get a time, set up a time together to go over whatever you're confused about. But we'll be in class on Wednesday at this time. And some of you will be in class with me because there's a few people that do not have a 70%. Although I will say many of you are very, very close to a 70% that are below 70. So it's not like we're going to have a huge amount of people that have to be here on Wednesday. And of course, you still got time between now and Wednesday to get that stuff turned in. Most of the people that have a low grade are missing items. They have zeros somewhere because they didn't turn it in. So if you get that turned in between now and Wednesday and it pushes your grade up, I'll count you present. So, alrighty. So how we doing now? Oh, we've got a lot of folks in here. We can probably get started. So let me put it up on the screen. Let's go to our grade screen as usual. That's where I suggest you start every week too. Go to the grade screen and look and see if you're missing anything and what's due. See, if you're missing anything, there'll be zeros here. If you see any zeros, then you need to get that turned in or turn in again. If you turned it in and got zero because you didn't get anything right, redo it. But this week, if we look at what is due this coming week, October 13th, we're doing 2.08 polynomial operations. And then we have a practice test because next week we're testing. So we're going to finish up this unit next week, which means after we test next week, if you're missing anything up here, it'll be gone forever. So get anything turned in from module 1. But we're working at 2.08 and we'll look at the practice test briefly. But that's going to be there available for you. Let's go back to the activity screen. So we're way down at the bottom. Oh, look, I have a video for the practice test. Mr. Brock takes the Algebra II 2.09 practice test. So you can go to that or after you take the practice test. You can't look at it until you take the practice test. Take the practice test yourself. And then if there's anything you struggled with, you can come back and watch me take the same test. And I'll explain how I get my answers on every single problem. But the practice test is here. Let's look how many problems we got. 23 problems, which should be larger than the test. But there is the problems we're going to be doing for the practice test this week. So you guys can do that. And then, like I said, if you have trouble with any of that, there's a video right here in Buzz of Mr. Brock taking the practice test. And you can go see what you missed, and I'll explain how to do it correctly if you don't understand it. But 2.08 polynomial operations, that's our lesson this week. And we have several videos to watch in this. And this one, little cute little cartoon character videos. I don't know if they make these videos themselves or what. They're really kind of goofy. They're not very high quality, but I kind of enjoy it. All right, let's start out.
Is everything okay in there?
I'm fine, Dad, but the picture I took during our Grand Canyon trip fell and the frame broke. The picture looks fine, but the frame is trashed.
That's all right. It can be replaced.
Okay, I'll go get a measuring tape.
I've got a better idea. Let's use your algebra skills to find the measurements. If you get the answer right, I'll buy you a new frame.
All right, I'll give it a shot.
Let's get started then. The picture is 3 times as long as it is wide.
Okay, so I'll make the width x, and then the length will be 3x. That means the area of the picture is x times 3x, or 3x squared.
Great start. I have a mat that should leave a 2-inch border around a photo that's 96 square inches. Let's see if you can figure out x now.
All right, that's my kind of dad. Makes you do some algebra rather than just getting the measuring tape. So anyway, broke the frame, got a 2-inch mat That'll go, so add 2 inches to every dimension there and figure out how big a frame is. And it's 96 square inches. So Taylor's got her work cut out for her. So let's see what we've got to help here. We're going to learn how can standard arithmetic operations be performed on polynomials and what similarities exist between operations on polynomials and operations on functions. All right, so let's talk about a closed system. This is some math terminology that's good to be familiar with. A closed system. So have you ever heard the expression that if it walks like a duck, sounds like a duck, it's probably a duck? Yeah. Well, the same can be said about math. When 2 integers are added, the sum will always be an integer. Always. If I add the integers 2 and 7 together, I'll get an integer as an answer, 9. And it sure says, don't believe it? Go ahead and try it. Even when 2 integers are subtracted or multiplied, the answer is always an integer. So any 2 integers, negative 11 times 1 is negative 11. That's an integer. If you add or subtract, 28 minus a negative 2, that's 30. That's an integer. So if you have 2 integers, whether you add them, whether you subtract them, whether you multiply them, you'll always end up with an integer. That means that system is closed for those operations. When you're dealing with integers with addition, subtraction, multiplication, that's a closed system because you can't get anything other than what's already in there, right? You're using integers and you're adding integers and you'll always end up with integers. So everything's still in the same place. It's closed system. You can't end up with a decimal. You can't end up with an irrational number. If you have an integer and you multiply it times another integer, you'll always end up with an integer. Now, it's not closed for division. It's only closed for addition, subtraction, multiplication, because division, if we have 13 divided by 2, those are 2 integers, but we end up with 6.5 as an answer, which is not an integer. So you have to classify that as just for those operations. So any integer added to an integer results in an integer. 3 plus 4 equals 7. Subtracted, 3 minus 4 is negative 1. Multiplied, negative 4 times 3 is negative 12. All integers. But there's no way to get a fraction or a decimal when you're doing those operations. But if you divide 3 divided by 4, see, now you've got 3/4, which is not an integer. Now, polynomials behave the same way. Polynomials. We can add them, subtract them, or multiply them, and we will always end up with a polynomial or 0, which like 0x, So polynomials are closed operations also for addition, subtraction, multiplication. It's going to be mechanically similar to what we did with complex numbers because we just got through adding complex numbers, multiplying complex numbers, subtracting complex numbers. We're going to do the same thing with just polynomials that do not have complex numbers. Adding polynomials. So the most important part is being able to identify like terms, right? Like terms. That's important. So I'm going to open up the chat so I can see you guys' input on here. We have these variables on the left, and over here is a set of like terms. So let me start with, let me blow this up a little bit to make sure you can see it pretty well too. Oh, that's pretty good. All right. Now you can see it better. If I start with 4f, which one of these is a like term that I could add it to or subtract it from, combine it with? 4f. What is the like term? Oh, you guys are quick on this. 7f. All right, let's click it and see if it disappears. It did. We were correct. How about 7gh to the fourth? How about that one? 7gh to the fourth. Oh, I see. Oh, you guys are on this. Can't put it on anything else. Huh? How about 3x squared y? Right there at the top. 3x squared y. Obviously, we can't put with the 4f squared. We can't put it with this 12xy. It's got x and y's. Nobody's saying we can put it with that. You're right, because x squared and x are different. They cannot be put together. So we have to go down here. 9x squared y. Same variables. X squared y, x squared y. 6xy. That's the other one we can put the 12xy. You guys are on that in a hurry. And how about the 8b to the third power, c to the second power? 8b to the third, c to the second. Yeah, the other one that has b's and c's. That has to be the third, c the second. This has to be the third, c the second, which just leaves those two right there. Good job. You can start over, but yeah, matching each one's. Good job. All right, let's shrink this back down a little bit. All right, so we're going to look at adding these two polynomials together. We have 7x squared plus 3x minus 5 being added to 2x squared minus 4x plus 9. So we have a video for that too. And it's all about distributing. You have to distribute because we have parentheses that we're dealing with here.
Start by distributing any coefficients to eliminate the parentheses. There is no integer or variable before either set of parentheses. Consequently, an understood 1 is put in its place.
So basically, you can just get rid of the parentheses since there's only ones outside of it. So that's what they're doing. It's just getting rid of the parentheses.
This leaves you with 7x squared plus 3x minus 5 plus 2x squared minus 4x plus 9. The next step is to identify the like terms in the expression, because those are the ones that can be combined. 7x squared and positive 2x squared are like terms. Positive 3x and negative 4x are also like terms. And the constants negative 5 and positive 9 are like terms. Combine those terms by combining their coefficients. Remember, the variable part stays the same. While it's perfectly acceptable to show the 1 in front of the x, it's not necessary since the 1 is understood. Just be sure to leave in the subtraction sign. The sum of the two given polynomials is 9x squared minus x plus 4.
And there's your answer. It's just as simple as combining like terms when you're adding them. We can add the x squared terms together, add the x terms together, and add the constants together to end up with 9x squared minus 4x plus 4. I'm betting a lot of you could have got that faster than a minute and a half, but they explained every step. It took them a while to get rid of the ones outside the parentheses. All right, pretty simple. Let's try another one. Oh, this is a pretty good one. I think we'll do this one on paper. Let me write this down real quick. All right, so if we're going to combine these, we're going to add these together. This polynomial added to this polynomial. We said it works a lot like complex numbers. Remember, with complex numbers, we had to add the real part to the real part and the imaginary part to the imaginary part. With this, it's similar, but we have to look and see. Let's see, here's a 2x to the third, right? That's x to the third. Well, it's not wanting to focus very well today. We can only combine that with other x to the thirds. So if we go over here, there are none. So that one's by itself. So that just comes down 2x to the third plus 0x to the thirds. There's not any over here. See if I can raise it up a little bit. Do something where it focuses a little better. All right. So then let's look at the next term. We have an x squared term. Well, here's an x squared term, and there's no other ones. That's an x constant. X. So we can combine the 4x squared plus 3x squared. And those terms are now done. So what's next? We have just an x, and this has just an x. So those are like terms. We have negative 1x, positive 6x. So altogether we have 5x. Then we just have the constants. 10 plus 7, 7 plus 10. So that would be our answer right there. Adding this to this, we can only combine like terms. So this one doesn't get changed. There's nothing added or subtracted from it. 2x to the third stays there. All right, let's look what they got. Distributing coefficients, which means there are no coefficients. You just get rid of the parentheses and then combine the like terms. So 2x to the third plus 7x squared plus 5x plus 17. That's what we came up with. All right, let's go to page 3. Subtracting is almost exactly like adding, but now you got to figure out there's that negative. This is like a -1. So we'd have to subtract everything or multiply everything by -1, and then we can combine them. So let's see, we've got a couple of videos or just one video on this page.
The first step of subtracting polynomials is to distribute any coefficients in front of the parentheses. There are no integers or variables before either set of parentheses. Consequently, an understood 1 is put in its place. When 1 is distributed to each term within the first set of parentheses, the trinomial within remains unchanged. However, a -1, instead of positive, is being distributed to each term within the second set of parentheses. This will change the second trinomial. Now that you've gotten rid of the parentheses, identify the like terms in the expression. 9x squared and -7x squared are like terms. Positive x and -3x are also like terms. And the constants, +2 and +4, are like terms. Combine these like terms by adding or subtracting coefficients and keeping the variable part the same. 9x squared minus 7x squared is 2x squared. 1x minus 3x is -2x. And 2 plus 4 is +6. And that's it. The difference of the two given polynomials is 2x squared minus 2x plus 6.
So yeah, we're just subtracting everything inside the parentheses over here. Subtracting the 7x squared, subtracting a 3x, and subtracting a -4. And when you subtract a negative, that means you add. So they just distributed that to show what we were doing with each term. Subtracting that, and adding that because it was already a negative. All right, and then we have another example down here. This one does not have an x to the third term in the first set. It only has an x squared. This, we're subtracting an x to the third. So if you distribute that, you got 4x squared minus 5, subtracting an x to the third, subtracting a 2x squared, and subtracting 7. So you end up with just a -x third out front. It was basically 0x third minus x to the third plus 2x squared minus 12. All right, if you didn't distribute the -1, you could end up with a problem. Show more experimenting with polynomial subtraction. Same type of thing there. If you didn't distribute, it shows how you would have got the wrong answer if you didn't take that negative through everything and just put it on the first term. See, if they didn't distribute it, they only subtracted this term. These they added. So we just got to remember we're subtracting everything inside the parentheses. Page 4. Using the distributive property. So multiplying polynomials. So let's see, there's multiplying by a monomial, binomial, and polynomial. So a monomial is just like multiplying 3x squared times everything in parentheses. So let's do that on paper, just to have that in our notes. Okay, we've got that right here. So all we have to do is just distribute this and multiply it times everything that's inside the parentheses. There's only one term outside. So 3x squared times 5x squared. Well, 3 times 5 is 15. X squared times x squared is x to the 4th, right? Because that's x squared times x squared, which square something you multiply by itself. So you basically just have 4 x's being multiplied times each other, x to the 4th. Then we got 3x squared times negative 7x. 3 times negative 7, x squared times x. Now you have 3 x's. And then finally times the 8. 8 times 3 is 24. X squared times 1, really, because it's x to the 0, which is 1. So when we multiply this monomial times this, we get 15x to the 4th minus 21x to the 3rd plus 24x squared. And as they go through the steps of that, times each one multiplied times each term, you finally get down to the end. They don't show what the final answer is. Oh, what's happening to the exponents? The same variable. If 2 or more of the same variable being multiplied, you add the exponents. Right, so they end up, here's the answer that we got, 15x to the 4th minus 21x to the 3rd plus 24x squared. Same thing with a binomial. You have to distribute both terms. The x has to be multiplied by both in the other parentheses, and the 6 has to be multiplied. I'm going to skip that one. You can go through it if you need, but I'm going to go to multiplying by any polynomial. So let's get one that's a little tougher. So this is how they have it written. So we'll do it in this order. But you could put the x minus 5 front and distribute it, but we're going to distribute the larger one into the smaller one. So it means we need to take the 4x squared and multiply it by x and multiply it by negative 5. So that's the first thing we distribute. 4x squared times x, 4x to the 3rd. 4x squared times negative 5 minus 20x squared. Okay, that's it. We've distributed that times everything in parentheses. Now we can go to the next term and multiply this times the first term and times the second term. So negative 5x times x. That's negative 5x squared. Negative 5x times negative 5. Negative 5 times negative 5 is a positive 25x. Negative 5x times negative 5. Okay, what's left? What's left? We got to take our last term, the 9's got to be multiplied by both terms. 9 times x. Oh, that's just 9 x's. 9 times negative 5, negative 45. Okay, so now we just look for like terms. That's the only x to the 3rd. We have 2x squareds. Those are both x squareds. And we have an x term and an x term. And then the constant's by itself. So just combine like terms. So this is 4x to the 3rd minus 20x squared and minus 5. So we've got minus 25 altogether. X squareds. We got 25 x's here and 9 x's there. When we add those together, we now have 34 x's minus 45. So that's it. Doesn't matter how big they get. We just distribute and then combine like terms. The process works the same regardless of how big the polynomial is. Up here we distributed and there wasn't any like terms to combine. So that's how the process works. So we're going to go through the whole steps there. You take the first 4x squared times x, and then 4x squared times negative 5. Then you go to the negative 5x times x, negative 5x squared, negative 5 times negative 5x times negative 5, positive 25x. And then the 9x, and the negative 45. And combining all that good stuff, 4x to the 3rd minus 25x squared plus 34x minus 45. Oh, let's look more at finding the dimensions of the picture. See how she did with her algebra problem.
Is everything okay in there?
I'm fine, Dad, but the picture I took during our Grand Canyon trip fell and the frame broke. The picture looks fine, but the frame is trashed.
That's all right. It can be replaced.
Okay, I'll go get
Okay, is it me or this daughter looked like she's like 45 years old? Okay, just checking. Make sure it wasn't just me.
a measuring tape.
I've got a better idea. Let's use your algebra skills to find the measurements. If you get the answer right, I'll buy you a new frame.
All right, I'll give it a shot.
Let's get started then. The picture is 3 times as long as it is wide.
Okay, so I'll make the width x, and then the length will be 3x. That means the area of the picture is x times 3x, or 3x squared.
Great start. I have a mat that should leave a 2-inch border around a photo that's 96 square inches. Let's see if you can figure out x now.
Well, the total area of the mat around the photo is 96 square inches. Now, if the mat has a 2-inch border, then the length of the mat is 4 inches more than the length of the photo. Also, the width is 4 inches longer than the width of the photo. Because area is length times width, the area of the mat is 3x plus 4 times x plus 4.
You're doing great so far. Keep it going.
Now I'll use FOIL to multiply the binomials. So the total area of the picture and mat is 3x squared plus 16x plus 16. This is also equal to the area of the mat plus the area of the picture, or 96 plus 3x squared. Now I just simplify. I got it! X is 5. The width of the picture is 5 inches. The length is 15 inches.
Awesome work! You earned your frame.
So either these are some little miniature 2-foot tall people, or that's not really to scale, because that picture looked a lot wider than 5 inches tall and 15 inches long, because it was like twice the size of her head. So her head must be like 2 or 3 inches. So yeah, those little cartoons amuse me. The math is good. The cartoon part's just kind of silly sometimes. But there we go. There's how you solve that. Okay, let's move on. All right, we're going to talk about some other terms here, functions. We're going to review this. So we're talking about functions and vertical line test and function notation, domain and range and all this kind of stuff, which is really kind of outside polynomial operations. I don't think there's any questions for any of this, but it's a good review. So let's look at these. X squared plus y squared equals 1. That's the equation of a circle. X plus 7 equals 10. That is just a up and down line when you graph that. Y equals 2x plus 3. This is just like a linear equation that has a positive slope. And y equals x squared minus 7x plus 6. That's a parabola. That's a quadratic equation, right? So y equals 2x plus 3 is the one we're most familiar with. And we know it's a function because let me remind you. Let me remind you what a function is, because we lose this. We forget it. A function means for every x that you put into the equation, you'll only get one y. When I take x and I put a number in for x, I'm only going to get one answer for y. Right? For that particular x, for any x. Which means if I graph it, if I put a vertical line and it touches the graph more than once, there must be 2 y's at that same x point, and it would not be a function. But if it only hits the graph one time, good, there's only one y for that x. So that vertical line test that you look at any graph, so if the graph shaped sideways like that, a vertical line would cross it twice, up here and down here. It would not be a function. 1 y for each x. Now you can have the same y, right? Maybe x equals 1, the y equals 2. And when x equals 2, the y equals 2. When x equals 3, the y equals 2. It's okay. They're all the same y. It's just a horizontal line. But each x only has one y. It's the same y, but he's only got one. I've only got one y. So that's fine. Just a nice review there on functions, rather than going through the way they talk about it on here. But let's go back. So it says, in order for an equation to be a function, there must be only one y value for each x value. So out of the 4 examples above, these 4 equations, 2 meet this requirement, and 2 of these are not functions. X squared plus y squared equals 1, it would graph a circle. A circle is not a function, because when you put an up and down line, you're going to hit the circle twice in many, many different x's. The other one that is not is the x plus 7 equals 10. It's a straight up and down line. It's one x with every y. Every y is assigned to that same x. But the linear and the parabola up here just has one y. So you can make a table, 2x plus 3. And every time you put an x in, there's only one y. -2 is 1. -1 is 1. 0 is 3. 1 is 5. 2 is 7. Never do you get 2 y's for any one number. Here's the parabola, same thing. -2, you get 24. -1, you get 14. 0, you get 6. 1, you get 0. -2, you get -4. That's fine. There's only one x value. Here's the circle. When -1, it just equals 0. That's fine. But when x is a half, I get 3 square root of 3 over 2 and negative square root of 3 over 2. When it's 0, I get 1 and -1. So there's 2 y's for the same x value, not a function. And this one graphs an up and down line at x equals 3. So every single y is mapped to the same x value. So that's definitely not a function. And then it talks about that vertical line test right here. If we had a function that went like that, complete drawing the function, put that vertical line, you put it down that end, it only touches it once. We moved on this end, and it only touches it once. Anywhere in between there, it only touches it once. So this is a function. Function notation, that's just where we replace the y with an f of x to name the function. So we can do that. So if, with function notation, like if we want to know what this equals when x equals -6, we can write it in function notation as f of -6. So that means replace x with -6 everywhere you find an x in this equation. So instead of 2x plus 3, it's 2 times -6 plus 3, which will simplify down to -9. So just as so you would not name all your pets the same name, different functions need different names. So using function notation, if we're dealing with more than one equation, we can call one f of x, the second one we could call g of x, the third one would be h of x. We can give all of our functions a different name. All right, here's more on function notation if you need more notes on that. Like finding f of 4. That means use the f of x function, but instead of x, replace all the x's with a 4. So instead of x squared, it'd be 4 squared. Instead of -8x, it's -8 times 4. Then you just do the math to find out that f of 4 equals -6. So that's how function notation works. You replace the y with f of x, just to give it a function name. This is function f of x instead of y equals. And domain and range. Domain is all the possible x's. The range is all the possible y's. So if they give us this domain, the only possible range are the y's that we get when we substitute these numbers in. So -3, -1, and +2. That would be the range, because this is what we said the domain is. All right, page 6. Inverses. Now we're going to get the inverses in the same lesson. So have you ever seen an inverted roller coaster? That's where the cars are underneath the track, hanging below the track instead of sitting on top of the track. If you haven't, go to Cedar Park, Ohio. They have 21 roller coasters there, and some of them are inverted. I've rode an inverted roller coaster. Pretty cool. An inverted airplane is one that flies upside down with the tail pointing downward. If you invert the colors on a photograph, it turns black colors into white and white colors to black. It totally switches all the color patterns. So inversion is the process of reversing the order or position of something. If you have an integer and you want to find the inverse, that means you perform an operation that cancels out the number. Like if you're given the number 7, you can add -7 to it, and that would cancel it out. 7 plus a -7 is 0. So that's finding the inverse of 7, would be -7. Or you can multiply 7 by the reciprocal of 1/7, and that just cancels that to be 1. So with equations and consequently functions, finding the inverse requires reversing the variables and solving for y. So we're going to do that. I'm not going to watch the video here. I'm going to write this down because we're going to go through the steps. And I'm going to start back from one step that they've got. To find inverse. So if you're a note person, this is great notes right here. Step 1. Change this from y equals, oh gosh, no, I did it backwards. Don't write that down. I'm just kidding. We would start out with function notation. They gave us this problem, f of x. This is the function. We're going to change it to y.
No, you had 5. You can't keep going. Nice try. Alani is next on my list here.
So step 1, change f of x to y. Same equation, f of x equals 3x minus 5, but now it's y equals 3x minus 5. Okay, step 2.
No, it might just be how I took the picture. That's not one of them.
X equals 3y minus 5.
That one out there?
Swap x and y. Did you see that? Did you catch that? The x became the y and the y became the x. I swapped them. So instead of y equals 3x, it's x equals 3y minus 5. Step 3. Solve for y. So we're going to get y by itself. So we're going to add 5 to both sides. So over here we got x plus 5 equals 3y. Divide it by 3. So y equals x plus 5, all divided by 3. Step 4.
Hang on, Connor.
Right in function notation again. We note the inverse by putting this little -1 up here. This is the inverse function, f of negative. This is the function. This is the inverse function. So these two functions are inverses of each other.
That's much better, dude.
3x minus 5, the inverse is x plus 5 minus 3. If this was your function, this would be the inverse.
Okay, you.
But if you have these 4 steps, change the f of x to y, swap the x and y, solve for y, and then write it back in function notation. But that's how you find the inverse. I'll leave that up for just a second. Handy to know, because we will deal with inverses the next couple of years here in math. Here's a video that should do the exact same thing. I won't play it all, but it takes you through all the steps and finally writes it as f of x at the end. The x plus 5 over 3 is the function, the inverse function of the original. So If you need to review that, there's a 1 minute and 7 second video that goes through the same thing I just did. Here's the good thing right here. Let's take a look at Desmos. Another thing we know about inverses is they create a reflection over the line y equals x. That's the line y equals x. And it's interesting that the inverse would do that because when we find the inverse, we trade the x and the y with each other. So it should not be a surprise that the inverse of the function makes a reflection over the y equals x line. There's the original function. Let's put the inverse in there. I got to use parentheses to keep the x plus 5 together on top of the fraction. But look there, it's a mirror reflection over that red line y equals x. So like if we have, let me find a point, this point right here, 7, 4. The point 7, 4 is on the line of the x plus 5 divided by 3, which means since we swap the x and y, if 7, 4 is on that line, 4, 7 should be on the other line. And it is. Because to find the inverse, we trade places with the x and y. So every x and y on this line, you can find the opposite on the other line. 4, 7, 7, 4. Let's see if we can find another one. Oh, what's this one? Is 2, 1 actually on the line? Oh, 2, 1 is on the line. So 2, 1 is on the line. So 1, 2 is on the line. On the other line, right? There they are. 1, 2, and 2, 1. Everyone that you can find, it's a mirror reflection over y equals x. That's the cool thing about functions and their inverses. So if we have these points that's on the function, 0, -5, 1, -2, and 2, 1, that means on the inverse, we'd find the exact opposite. -5, 0, -2, 1, and 1, 2. All you have to do is trade places. Okay, here's one's a little trickier. What if we have this function? Just x squared. That's it, just x squared. So the first thing we do is replace f of x with y. So it's y equals. Then we're going to trade places with the x and y. See, now it's x equals y squared. I'll make this a little bigger too because it's pretty small on the screen. There it is. First step, we replace the f of x with the y. Step 2, we trade the x and y. Step 3, we solve for y now, which means we need to take the square root of both sides. So y would be the square root of x, plus or minus, plus the square root of x and minus the square root of x. Then we'll go back to function notation. What's step 5? Step 5 is just looking at the graph. Here's the graph of the inverse. The inverse is plus or minus the square root of x. But here's the problem. The inverse of the function is not a function. It does not pass the vertical line test. When x is 2, there's a y up here at 1 point something and another y down here at -1 point something. This is not a function. So even though we can calculate the inverse of a function, it does not mean that the inverse is a function. Ooh, that's kind of tricky. It does have an inverse, but the inverse is not a function. This equation is not a function. All right. Solving inverses of functions. So here's another one for you to try. I'll leave that. We can try that with those 4 steps where you swap to the y, trade places with the x and the y, and then solve that for y. So not every function has an inverse that is a function. It may have an inverse, but it doesn't necessarily make a function because of that problem right there. Now, we can restrict the domain of the original function. Let's graph that and look what are we talking about. We said y equals x squared does have an inverse, and the inverse is y equals plus or minus the square root of x. Oh, actually, it did plus and minus. Let's see.
20% for Zoe.
It's almost like two graphs. Y equals the square root of x. See, that's the inverse, but it's not a function. But if we went to the original and we said, let's see, how can we restrict that? X is greater than or equal to 0. If we only look when x is greater than or equal to 0, we could also do that here.
Say it again.
I'm only doing the positive x's
I have to. Good job.
or 0. 0, 0 is included.
You're gonna come again?
So if I restrict the domain, I said I'm only looking when x is greater than 0, then there's an inverse function. Otherwise, the inverse is not a function. So that's what that's talking about right there.
She's on the meat.
If you restrict it to numbers greater than or equal to 0 only, then you can make it a function inverse. All right,
It's
what's
like
here?
this, ready?
Page 7. Equations versus functions.
You're all my favorite.
Okay. At this point, you've learned what makes an equation a function. Remember, every x only has one y. So the graph passes the vertical line test. So instead of writing y equals all the time, though, we should be just as comfortable writing f of x equals, because it means the exact same thing. It just gives the function a name. We can call it f of x, g of x, h of x, d of x, b of x, c of whatever we want to call it. And then we call it f of x. All right, so f of x means substitute the value of x into a function f. It means whatever it is. So now that we have a handle on function notation, let's add, subtract, and multiply some functions. All right. Let's see what we did before. We did a little multiplying, subtraction. It wants to do a few more practice. But we can give them different names now. See, that's the difference. That's the difference. So let me switch over to here. See, now the difference is that we can take f of x and give it a name, and we'll say it's 3x minus 4. And then we can take g of x
Patrick is the same to me that you
and
are.
give it a name of 5x plus 1. And we have two different functions. Oh, sorry. Let me move that down where you can see it. Two different functions. So we can do f plus g of x, which means we just take f of x and we add it to g of x, which would mean we take 3x minus 4 plus, I put that in parentheses, 5x plus 1, which would be 3x plus 5x, 8x, negative 4 plus 1. So that's what f plus g of x is, 8x minus 3, because I add the x's together, I add the numbers together. I can do f minus g of x, which just says take f of x and subtract g of x. See, function notations allows us just to use the same two functions. Instead of y equals and y equals, I'd have to tell you what you need to do. With this, I can just name them and say, okay, add them, subtract them. So this would be 3x minus 4 minus 5x plus 1. 3x minus 5x, negative 4 minus 1. That also gives me the opportunity to say this. How about g minus f of x? That's just changing places. We're subtracting f from g. So this would be 5x plus 1 minus 3x minus 4. I just went the other way. I just swapped them. So 5x minus 3x would be a positive 2x. 1 minus a negative 4 would be positive. Look, we got the same answer, just different signs. Because first we subtracted that one from this one, and then we subtracted this one from that one. And we could also do f times g of x. F times g. So that just means take g of x. Well, I guess I should write f first since I wrote it first over there. F of x times g of x. So that means I'm going to take 3x minus 4, and I'm going to multiply it times 5x plus 1. So 3 times 5, 3x times 5x is 15x squared, 3x times 1, 3x, negative 4 times 5, negative 4 times 1. These are like terms, so it's 15x squared minus, not 20. I've got 3x minus 20x minus 17x minus 4. So that's what we're really talking about. Getting function notation just allows us to name them and then use them for several problems. I don't know what all examples they did. Let's take a look. They had 4x minus 7 and 10x minus 3. And then they did a lot of the same stuff. This was adding them together. This is subtracting them, multiplying them, distributing to get different answers. But just using the same f of x times g of x, same f of x, g of x. So different functions can be, different results can be found by putting different operations on the same two functions. Yeah, I mean, look what we had here. Same two functions, but we got many different answers. Whether we add them, subtract them, multiply them, which we would expect. That should not surprise anyone. And then the last thing I want to look at, I think, is here's a lesson summary right here. Verifying inverses. We need to do that too. Function composition. So there's one more that we did not do right here. F of g of x. You're like, well, that looks a little different. Yeah, because where's g of x this time? It is inside the parentheses. The g of x is inside these parentheses. That's where the x usually is. But we put g of x in there. So what does that mean? Well, that means we take g of x and substitute it in for the x. Instead of 3x, it's 3 times 5x plus 1 minus 4. So that's the exact same equation as that one is. The equation hasn't changed. The only thing that changed was instead of x, we substituted g of x, which is right there, 5x plus 1. So it takes the place of x because we said f of g of x means to take g of x and substitute it in. And that's going to equal 3 times 5x, 15x, 3 times 1. And then we still have this minus 4 at the end. So it equals 15x minus 1. That's the only like terms right there, right? So again, different answer than all these other things, but we can do f of g of x. And of course, you can do g of f of x. And it'll be different. Because now we're taking 5x and we're substituting this in for x. It'll be different. All right, so the last thing we're going to look at then regarding these, and I don't know if we're going to have a problem that does this. But I know in Algebra 3 we'll do some of this, so I wouldn't be surprised if we do some in here. Let's go back and look at those inverses that we had over here. 3x minus 5, x plus 5 over 3. So if f of x is 3x minus 5, and g of x is x plus 5 over 3,
not the entire email.
you may have a problem that says,
Well done, ma'am. It's like our little
prove, oh man, we're back to geometry. Prove these are inverses. How do we prove that? We think, well, if I graph them, they should reflect over that. Yes, but that's not a proof. A proof, they want it algebraically. So here's what we do. We take f of g of x first. Okay, so we're going to take this. Instead of x, we're substituting g of x. Minus 5. Okay, see what we did? We just took g of x, equals. We just took g of x and we substituted it in for x. So let's simplify this now. If I have x plus 5 divided by 3 multiplied by 3. Wait a minute, I said divided by 3 multiplied by 3. Doesn't that cancel each other out? If I divide by 3 and multiply by 3? Yes, it does. That just leaves x plus 5. And then we have the minus 5 outside the parentheses. X plus 5 minus 5. Wait a minute. Plus 5 minus 5. Doesn't that cancel each other out? That just equals x. So when we substitute g of x into f of x, it's just x once we simplify it. Let's go the other way. We're going to take f of x and we're going to substitute it into g of x. X plus 5. So this is going to be 3x minus 5 plus 5 over 3. Right? Doesn't that look just like g of x, except for we've taken out x and put in f of x? Okay, let's simplify this. Well, the parentheses can just go away because there's just a 1 outside. There's nothing there. So 3x minus 5 plus 5. Minus 5 plus 5. So that's just 3x. Divided by 3. Right? 3 divided by 3 is just 1. Look at that. That simplifies to just x. Well, when we put g of x into f, it's simplified to x. When we put f of x into g, it simplifies into x. That proves it. They are inverses. If they both simplify to x, that proves it. They're inverses. That's how you prove it. When it says prove that these two functions are inverses, or if it asks, are these function inverses, this is what you do. You substitute g of x into f, and you substitute f of x into g, and simplify them, and see, do they both equal x? And if they do both equal x, that proves it. They are inverses. Wow. Okay, algebraic proof to show two different functions are inverses of one another by substituting into each other. So it talks about that down here in the lesson. Verifying inverses. So here it is, the 3x minus 5. That's the same equation I had in the x plus 5 over 3. So function composition, where you take one and substitute in the others. If f of g of x equals the same thing that g of f of x is, which is x, then that proves that they're inverses. So here's where they substituted f of g of x, where they took the g of x and put it into the first equation. Which way did they do theirs? They put, I had them back. I had g of x being this one and f of x being this, but it doesn't matter because we're using the same two equations. But when they simplify it all the way down, it equals x. And it works both ways. Oh, they did, yeah. There's the first one equaling x. There's the second one equaling x. So they went the other way right here, g of f of x. So here's one for you to practice yourself. X minus 2 over 6 and 6x plus 2. Verify that those are inverses by substituting f of g of x and g of f of x. Both ways. After you do that, if it equals x, you're good. If not, see what you did wrong. See where you messed up, because they should equal x. Lesson summary. Oh, finally, we've been looking for that lesson summary for an hour. Adding polynomials. Distribute any coefficients if there's a number out in front, but there's not. Combine like terms. Subtract, combine like terms. Multiply, you're just distributing each term basically, and then adding any like terms together. Here's the function composition where we take f of g of x. That means substitute g of x into the f. And then it talks about the operations. To add two functions, you can use this notation, f of x plus g of x. To subtract, f of x minus g of x, or f of x times g of x, and then there's that f of g of x. They have 2 pages of practice problems for you. Add these polynomial expressions. Which one of those is the answer? 4 problems. Then you click here. Subtract these. Which is the answer? 4 problems. Multiply. Then you can check your own work right here. And they have 9 problems. Look, starting out with just simple, just a 4x squared outside the parentheses. But it gets more complicated. Now you got 3x and a 5x and a trinomial, 2 binomials, 2 binomials, 2 binomials, x minus 11 squared. That's 2 binomials. It's x minus 11 times x minus 11. Same thing, 2x plus 5 squared. And here's a trinomial being multiplied by a binomial. 3 terms, 2 terms. Okay, what's over here? Oh, here's find, with these 2 functions, find f plus x, f of x plus g of x minus f of x, and f of x times g of x. Be careful there. They put the g first. We're subtracting the f. So which one of the, here's one of the answers. Which one would it be? That one? That one? That one? Yay, it shows you how to do those. And they got 3 of those. 3 of those. All right, then the last page of practice.
Open up your email, man.
Activity 1 and activity 2. Select the solution to the problem. If you take this one and add this one, which one of those do you get? There's 6 of those. Over here. Here's what f of x is. Here's what g of x is. What are they when you add them together? And then you can go over here. What are they when you subtract them? What are they when you multiply them? Multiply them again. And finally, g of f of x. Substituting f into the g. And everywhere else you check your answers. All right, let's look at the assignment that goes with this. Adding 2 trinomials. Subtracting f of x minus g of x. Multiplying. Which of the following represents the area of a triangle has this length and this width? Which just means you're multiplying those together. Multiplying f of x times g of x. Multiplying 3x minus 5 times itself. That's what squared is. Remember, you're just multiplying 3x minus 5 times 3x minus 5. Multiplying those. This one and this one. Find them when you multiply them together. And here is the base price for a football game as modeled by this function. That's a base price. Where X is the year since the team started playing football. So every year it goes up $15. Not included is the service charge of this. So if you wanted to find the total cost, what should you do? If this is the price of tickets and this is the service cost, are you going to add those, subtract those, multiply those, or it cannot be determined? Spoiler alert, it's not, it cannot be determined. All right. That's your assignment. That and the practice tests. Like I said, we got the practice test next. After you do the practice test, if you struggle with any of it, watch my video. Watch my video. I'm just going to, oh, that's messing up. That's better. That looks much better. Woo. All right. That looks much better. So let's see if I just turn something in so I can go look at it. I missed it. Go back. Now you can look at the practice test. After you turn in the practice test, you can look at the video for the practice test. And here's the video where I take the practice test. It's 45 minutes long. but I do every single problem and explain every single problem. Here I am working them on paper and explain how to get them. So if you struggle with any of that, you can maximize that too, make the full screen. If you struggle with any of that, you don't have to watch the whole 45 minutes, because if you did the first 10 with no problem, skip the first 10. Don't watch me do the first 10 if you got all those right. Where am I at? I'm on number 12 right there. So just go look at the problems you need help with. Just look at the problems you need help with. So, all right. At the end. Computer's running sluggish today. It's probably because we have so many people in this class, which is fine. That's all right. We're good. All right, guys. Practice test this week. That means the test is next week. So this is a good chance to figure out what you need to study before next week. Remember, the practice test is a practice grade. So you can take it as many times as you want to. It does not affect your grade. But take it and figure out what you need to study. That's what the practice test is good for. If you nail the first 10, that means you probably know the first couple of lessons. It'll tell you which lesson each problem says. This is from lesson 2.03. This is from lesson 2.01. Tells you, oh, I missed all the ones on 2.04. That's the lesson I need to go back and look at because I didn't know what I was doing. Because next week we'll get that test. You can use notes on the test. You can use notes on the practice test. You can use notes on any assignment. You can use notes on the semester final at the end of December. Always. That's why I encourage you to always take notes. Write down practice problems so you have something to look at when you have a problem on the test. Oh, I have a practice problem just like that. Let me see how did I do that? Okay, this is my first step. So let me work that with this. Notes are always great. Always allowed to use your notes. So, all right, you got about 15 minutes left of class if you want to get started on any of this. Otherwise, it is a B-Day Friday. We'll only have class on Wednesday. For those of you that have to be here, I'll see you Wednesday. For those of you who just want to be here, come see me Wednesday. All right, guys, have a great day. Go conquer the rest of your day.